Hello there, welcome to Everything Polar Coordinates, level 5. This is going to be the last video of this little mini-series. We're going to be discussing the Laplacian, Jacobian, cross products, and curl. Okay, so a little bit of housekeeping before we get this video started. So one of my objectives in working on this little mini-series was to, put together a coordinate systems equation sheet in LaTeX. That's around 70% complete. It's going to contain equations for, basically everything we've discussed so far in this little mini-series, but for Cartesian, polar, cylindrical, and spherical coordinates, okay? There's going to be about 64 items total on it. And of course, these are going to be the last couple here. Really, the Laplacian, Jacobian, and equation for curl is going to also be on that equation sheet for, each of the four coordinate systems, right? And it's very important for me to get that equation sheet done because here's what it's going to do. It's going to help me streamline my videos, get video times down, and focus, more on the physics as opposed to, the coordinate system that I'm working in, right? So I'm just going to be able to use the ideas for my given coordinate system as opposed to feeling like I have to explain where these, ideas come from and what they mean, right? And of course, I want to provide this sheet because I don't just want to pull, these equations out of nowhere. I want you guys to have a resource where you feel like, oh, okay, Mayday is saying volume element in spherical coordinates. I know what that means. I can go and I can look at the sheet. There it is, right? So I think it'll be a really helpful tool for all of us. So I'll be posting a link to this, little equation sheet in future videos. But of course, I'll talk about that once I actually have this done. Okay, but let's go ahead and wrap up these ideas. I'm going to go ahead and start with the Laplacian. It looks like this. It looks like a little nabla squared, right? And when we operate it on a scalar function f, this is of multiple coordinates, right, of r theta for polar coordinates, right? We can think of it as this is a generalization. It's a generalization of the second derivative for multivariable functions. Okay, and specifically, right? Specifically, we can think of it as literally like taking the nabla operator and dotting it with itself. So if we take that literally, right, then we have I'm applying it to this function f here. So we have nabla dot, right, nabla acting on f. We can think of this as, grad f here. This is the gradient of my function f. And so we're taking the divergence, right, of the gradient of my function f. Okay, so if I were to write this out, right, we could think of this, right? Here's the gradient part. So it's like I'm taking the divergence of the gradient of my function f when I apply the Laplacian on it. Now, why is this a very useful generalization of the second derivative, for multivariable functions? That's something we're going to have to see as we do more physics, okay? But we're going to go ahead and use this kind of definition here to come up with what the Laplacian operator looks like in polar coordinates, because we already know the gradient in polar coordinates and we already know the divergence. Alright, and since we derived these guys in earlier videos, now this is going to be super easy to come up with a Laplacian, right? So I'm just literally going to plug in for f of r here in my divergence expression. We're just going to plug in, the component, in the r direction from my gradient, right? And same deal, here. It's going to be really quick. So I have 1 over r d dr of r times df dr plus 1 over r d of 1 over r df d theta d theta. And now we just expand this all out, right? Just a little bit of product rule. So I'm going to go ahead and have 1 over r, start with the derivative of r, so this is just going to be df dr plus, now product rule it, right? So this r here is going to cancel with this r here. We're going to have d squared f dr squared plus, what happens if I take the derivative of 1 over r with respect to theta? That's going to give me 0, okay? So plus 0 plus, and now, second part of the product rule, this is going to give me 1 over r squared d squared f d theta squared, okay? All I did was the product rule. Okay, and now we just have 3 terms here. Let's go ahead and group them together nicely. So I'm going to have 1 over r d dr r df dr plus 1 over r squared d squared f d theta squared. Okay, and this is the Laplacian of a function in polar coordinates. So see how easy that is? We just used the gradient and divergence together. Nice and simple. So next, let's go ahead and talk a little bit about the Jacobian matrix. This is just going to be a brief summary. Okay, so a Jacobian matrix you can really think of at a surface level as just relating the rates of change between 2 coordinate systems, right? So here I have an example of a Jacobian matrix in 3D space, because we deal with up to 3D. If I introduced a new coordinate system comprised of coordinates gammas 1, 2, and 3, right, this is basically telling you every corresponding rate of change for my Cartesian coordinates x, y, and z for some arbitrary change in gamma 1, gamma 2, gamma 3, right? So it's very useful for a lot of things, linearization, it's a useful transformation matrix, and it's also useful for computing area and volume elements. I'll go ahead and talk about that in a second, but let's go ahead and just really quickly calculate this out. So in our case, really we have 2 coordinates, so like gamma 1 would really go to r and gamma 2 would go to theta. So we go ahead and we have dx dr dx d theta dy dr dy d theta. Okay, and all that we need to recall is our expression for x in terms of r and theta, which was x equals r cos theta, and y in terms of r and theta, which is r sine theta. And now we have everything we need to compute this out. What is d r cos theta? I'm just literally plugging this guy in for x here. What is dr cos theta with respect to r? Oh, that's just going to give us cos theta. Next, what is dr cos theta with respect to theta? Oh, that's just minus r sine theta. All right, next let's go ahead and plug in for y here. What is dr sine theta with respect to r? That's just going to give us sine theta. And what is dr sine theta with respect to theta? That's just going to give us, r cos theta. And we package this all together in one matrix. Cos theta minus r sine theta, and r cos theta. We can talk about more useful properties of Jacobian matrices in the future, but let's go ahead and start with one application real quick, right? We can really easily formulate, our area element, which we did purely geometrically, in the first video of this little mini series actually, right? We came up with the fact that dA in polar coordinates was equal to, r dr d theta. We can actually write this more generally for any coordinate system as equal to the determinant of your Jacobian matrix, as a function of, those coordinates, in this case, r and theta, right? Dr d theta. So let's go ahead and just confirm this fact to be true. Again, I'm not proving this fact, but, we're just going to take this as true. So let's go ahead and check this out. If I go ahead and take this, cos theta minus r sine theta, r cos theta. Let's take the determinant of this. We're going to have r cos squared theta plus r sine squared theta. And of course, cos squared theta plus sine squared theta is just 1. So we're going to be left with r. Okay, and so we can see, we get out our original area element that we computed geometrically, right? So this logic here applies to both area and volume elements. You can go ahead and use this kind of nice Jacobian determinant. All right, so lastly, let's go ahead and talk a little bit about the cross product, and then we'll go ahead and wrap up this series with curl. Okay, so if I have a cross product between two arbitrary vectors, v1 cross v2, right, in Euclidean space, again, we're not really talking about polar coordinates here, this is just a general definition. They have some angle theta between them. Alright, so the cross product is just defined as taking the magnitude of v1 times the magnitude of v2 times the sine of the angle between those vectors, and then we encode this into a vector that points in the n hat direction, where n hat is determined by, a convention called the right-hand rule. The right-hand rule. Okay, so first off, like, why are we even going through this? Why is this definition useful? Right, go ahead and think real quick about the dot product. Like if we were to take the dot product of these guys, we remember that output a scalar like v1, v2 cos theta. Think about why we could have this guy just output as a scalar, right? Let's go ahead and remember how this worked. If I projected v1 onto v2, right? And in this situation, these these projections kind of line up with each other. So the point being that if the similarity between our two vectors point in the same direction, it gives us a positive value. And if they point in opposite directions, it gives us a negative value. There's no ambiguity there, right? You can only have plus and you can have minus, okay? The objective with the cross product is to do the complete opposite of that. It's to say, find the components of my vectors that are perpendicular to each other, and then multiply those components, right? So literally here, this guy, this component of v1 would be v1 sine theta, right? And of course, if we take v1 sine theta times v2, we get the magnitude of our cross product. But there's an infinite number of ways that vectors can be perpendicular to each other, right? So if I have, let's just go ahead and call this guy A, right? B could be perpendicular to A like this, right? B could be completely pointing out of the page, and it's still perpendicular to A. B could be pointing down, right? We could go all like 360 degrees. You kind of see like this circle that I'm making here in the ZX plane, right? B can be perpendicular to A in an infinite number of ways. Okay, so the way we kind of encode how exactly are things perpendicular to each other, we add this little unit vector that's going to, basically determine the plane that v1 and v2 are trapped in. Okay, and it's a little bit hard for me to demonstrate. I can't exactly show my hand in this video format. So here's what I'm going to imagine. I'm going to go ahead and imagine I'm taking my right hand. Okay, so here's my right hand. Here's the start of my knuckles right here. Okay, and I start at v1. Okay, because I'm starting by crossing v1, cross v2. So I start at v1, and I take my fingers, and I kind of curl them like this. All right, I'm going to curl them just like this. Okay, so this is kind of what my hand's going to look like with my fingers kind of curling in this direction. Right, do you see that? Go ahead and line it up yourself. Right, and if you orient your hand like this with your, your four fingers, your index through your pinky finger pointing like this, right, then your thumb, if you're pointing your thumb outwards, is going to be pointing into the page right now. Okay, so that would be our n hat direction here. Here's n hat. So as you can see here, this operation is really only defined for 3D space, because you're always outputting a vector that's perpendicular to two other vectors. Okay, so you always kind of utilize all three of your dimensions. Now obviously if you're stuck in 2D, like you're thinking just purely about the Euclidean plane and not all of Euclidean 3D space, then you don't have all three directions to work with. Alright, in which case you can just define the cross product to output scalars, either plus or minus. Okay, which I'll go ahead and emphasize in a little bit. All right, so the next thing that we need to think about, just very similarly to how we thought about this for, the dot product, we need to think about what expressions for cross product of orthonormal basis vectors look like, because in physics, we basically always write our vectors in terms of orthonormal basis vectors, which again, we talked about in the last video. Okay, so what happens if I take two identical basis vectors and cross them? So like x hat cross x hat. Well, obviously this is just going to give me 0, right? Just to make this super duper clear, if I have two basis vectors pointing in the same direction, right, the sine of the angle between them, sine 0, just equals 0, so their cross product zeroes out. So that's a very good rule. Let's go ahead and, sticking to my kind of Cartesian examples, let's say that we have like x hat like this, y hat like this, and z hat like this. What would x hat cross y hat give us? Well, if you kind of go ahead and do the right hand rule, you'll go ahead and see that this points in the z hat direction, right? And likewise, you'll find that y hat cross x hat will give you minus z hat. Okay, so you can see that the order in which I do these kind of cross product of my orthonormal basis vectors is going to be really important, right? So this is kind of to summarize. I'm not going to go through the most general way I did it, like I did with the Kronecker delta notation that I had in the last video, but you can kind of see the rules of the game here, right? So there's two things that we can see, and these are kind of the two rules to remember. Taking 2 out of the 3 basis vectors and crossing them together is going to output the third basis vector. And depending on the permutation of how you cross them, that's going to determine the sign. If, that third basis vector is either going to be plus or minus. So we can kind of summarize these in, diagrams like this, like boom, 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 and here. And we put a little +1 in the middle, okay? So we can have these little pictures, like this, that remind us that, oh, okay, if I have my basis vectors being crossed in some order that goes along in this little cycle here, I'm going to get a +1. So, like y hat cross x hat, for example, right, goes against this kind of cycle here, and so it's going to give us a minus z hat. What about if I have z hat cross x hat, right? Z hat cross x hat is then just going to give us positive y hat because we're going with the cycle, right? And it's really easy to see alphabetically for x, y, and z because you can literally find in your cross product, like if you find a starting point and you can read out like x, y, z, right? I have this x, y, z. Here I have x to z to y. Ooh, that doesn't go in alphabetical order. That's gonna give you a minus sign. And it would be criminal of me not to show this last bit here, that you can use these relations, to come up with a very general, like nice and easy formula to calculate out cross products in Cartesian coordinates. All you have to do, you just throw in your unit vectors in the top row, you throw in the x component, y component, and z component of your first vector in the second, and the x, y, and z component of your second vector in the third row, right? If you just take that determinant, it's going to give you the cross product in Cartesian coordinates. Okay, and as I mentioned earlier, right, for this video we're dealing with polar coordinates, which is a 2D coordinate system. So for 2D, we lack a third dimension to put our resulting cross product vector into, so we just output scalars instead. So in polar coordinates, r hat cross theta hat, we can just say that this equals 1, and theta hat cross r hat is equal to -1. We're not outputting vectors anymore because we're just stuck in 2D and we don't have a third direction to work with. Alright, and using the cross product, notationally we can come up with the notion of the curl of a vector field. So this is very similar to the discussion that I had of divergence, but I'm going to go into a little bit less detail this time. So if I have a vector field, call it f, then the curl of that vector field we can define as the Nabla operator crossed with f. You have to prove this. By the way, what does curl even mean? It's the infinitesimal circulation of your field f which in order to properly define this, I have to actually define what circulation is. I'd have to define it, just like how I defined the notion of flux before I was able to properly define divergence. I might do this in another video, but for right now, let's just stick with the colloquial kind of meaning. It describes, the tendency of your field to rotate, aka curl, right? So, thinking extremely binary, if the curl of your field is equal to 0, you describe this as an irrotational vector field, which happens to be very important, okay? Right? I'm not going to go through and rigorously, define how we get curl from circulation. That would take way too much time. Maybe we'll do this later on, but let's just go ahead. This is the last definition for this little set of videos, and it's, another very useful one. So let's go ahead and come up with this in polar coordinates. So, all right, and then recalling the expression for nabla we came up with, along with the expression for our vector field F, right, just broken into a radial component and a theta hat component. Then we can go ahead and write this out as, just plug right in, ddr r hat plus 1 over r dd theta theta hat, and we're crossing this, right, with fr r hat plus f theta theta hat. And remember, just like I emphasized before when we did this for divergence, you have to take your derivatives first. You have to put the entire expression, because your hat vectors are, coordinate dependent. You have to get those derivatives first and then cross at the end. Okay, so let's go ahead and do just that. So we can go ahead and write this guy out as equal to, let's start with this guy here. So r hat cross ddr of fr r hat plus r hat cross ddr of f theta in the theta hat direction plus theta hat over r cross dd theta of fr r hat plus theta hat over r cross dd theta of f theta in the theta hat direction. Alright, and now we're back up. We have 4 terms again. We would have to, effectively product rule this guy out. Alright, so that's going to go ahead and equal this, right? Once I expand everything out, let's go ahead and just figure out what terms we, don't care about. Okay, let's go through one at a time. R hat cross R hat. Okay, that's going to go to 0. I don't care about this guy. Okay, next. Dr hat dr, derivative of r hat with respect to r. There are no r's in r hat. This is going to give us 0. Okay. Next over here, r hat cross theta hat is going to give us 1, so no problems there. We're going to want to keep this term. D theta hat with respect to r, that's going to give us something that looks like an r hat, and r hat cross r hat is 0, so we can get rid of this guy. Okay, next, what about here? R hat cross theta hat, ooh, that's going to give us like a -1. We need to keep that. Dr hat d theta, that's going to give us like a theta hat term, that's going to cross with the other theta hat to give us 0. Get rid of you. Theta hat cross theta hat, get rid of you. And then this guy we need to keep because it's going to output, d theta hat dr, specifically it's going to output minus r hat if you went through and calculated that out, as we have many times now. And let's just go ahead and write out our results, right? R hat, right? R hat cross this first term, r hat cross theta hat is just 1, so this is going to give us df theta dr. All right, next, theta hat cross r hat is going to give us -1, so we have minus 1 over r dfr d theta. Okay, and theta hat cross minus r hat. Okay, double negative kind of going on here. Theta hat cross r hat -1, but minus times minus is a plus, so we have plus 1 over r right, times, oh, this is just f theta left over. Interesting. So really we have just f theta over r. Cool. All right, and we can combine our terms together and kind of write things looking like this. We can write out 1 over r times d of f theta r dr minus dfr d theta. We can put it all together like this. And so now we have this expression for curl in this 2D polar coordinate system. But bear in mind for, 3D coordinate systems, your curls would be vectorial in nature and not scalars like this guy. Okay, but that's how you would go through and calculate that out. All right, I'm going to go ahead and end this video here. From this point forward, I'm going to try and wrap up that equations sheet. And then we're going to have all of these, coordinate concepts on paper, and then we're going to get to, more physics, and things are going to be streamlined faster, and, I think things are going to get pretty fun. If you enjoyed this video, consider subscribing to the channel, and, let me know in the comments. I love to hear about people getting on board. But other than that, thank you so much for watching.